All right, let's just get this out of the way. Mars. For generations, it's been the planet that sparks our imagination. The one we gaze at and wonder, is anyone or anything out there? From H.G. Wells's terrifying Martians to Ray Bradbury's lyrical chronicles, the red planet has always been humanity's cosmic mirror, reflecting our deepest hopes and fears about life beyond Earth. And let's be honest, we've had our hearts broken a few times, haven't we? Those fleeting glimpses, those tantalizing hints, only to have them dissolve under closer scientific scrutiny. It's like the universe has been playing a cruel game of peekaboo with our biological aspirations. But what if I told you that the game just changed? What if the universe, for the first time, isn't just teasing us, but is actually leaning in, whispering a secret that could redefine everything we thought we knew? Just a few short days ago, NASA's indefatigable Perseverance rover, our robotic proxy on that dusty red world, beamed back data that didn't just nudge the needle, it slammed it from a wistful maybe someday to a jaw-dropping quite possibly right now. 3 unassuming tiny gray rocks, given the evocative nicknames Chayava Falls, Sapphire Canyon, and yes, leopard spots, have delivered the strongest chemical hints of biology ever detected beyond our home planet. If you've been waiting your entire life, holding your breath for that epic-making sentence, "We may have found life on Mars," well, consider the ink officially dried. This isn't just another headline. This is a seismic shift in our cosmic narrative. This is different. This feels profoundly different. Why Jezero Crater was the perfect trap. So how did we get here? Why Jezero Crater? It's not just some random Martian divot. It's a 28-mile-wide geological masterpiece, a fossilized river delta that once spilled into a vast lake. Think about it like this. Imagine the mighty Mississippi River, but instead of flowing into the Gulf of Mexico, it's dumping its rich, nutrient-laden sludge into a Martian lake. And then roughly 3.8 billion years ago, that lake dried up and the entire delta was essentially flash frozen, locked away under layers of volcanic ash and cosmic dust. This wasn't just any old Martian puddle. This was a dynamic, watery environment, a bustling ancient ecosystem waiting to happen. Rivers, like the one that fed Jezero, are incredible transporters of organic material and minerals. They carry sediment, clay, and dissolve nutrients from vast drainage basins, depositing them in quieter lake beds. And those lake beds, they're perfect traps for life, if it ever existed. Any microbial life thriving in that water, any tiny organisms clinging to the sediments would have been buried, mineralized, and essentially locked away in a geological time capsule. That's precisely why Perseverance, a marvel of engineering designed to seek out signs of ancient microbial life, landed there in February 2021. The rover's mission was to explore this ancient river delta, a place scientists had identified from orbit as having once contained liquid water and potentially hosted habitable environments. What we know about early Earth tells us that such environments are the cradles of life. Fine-grained sediments and clays are particularly good at preserving organic molecules and even microfossils. Over its 3 solid Earth years on Mars, Perseverance has been diligently driving upstream along the remnants of that ancient river bar, drilling into every intriguing change in rock color, much like a meticulous detective, or as I like to think, a very persistent terrier sniffing out every lamppost on its beat. The rover has already collected 27 rock cores, and the latest findings from Chayava Falls and Sapphire Canyon are undoubtedly the most compelling. New research even suggests that Jezero Crater experienced multiple periods of habitability, shifting from initially hot and acidic conditions to cooler, more easily habitable ones later on. This means the window for life to emerge and thrive wasn't just a brief flicker, but potentially a series of opportunities, making it an even more promising hunting ground for biosignatures. The rocks that refuse to be boring. Now let's talk about these rocks, because honestly, they look pretty mundane at first glance. Take Chayaba Falls, for instance. To the naked eye, it's just a dark gray rock crisscrossed with millimeter-sized white veins. Nothing to write home about, right? But oh, how deceiving appearances can be. When Perseverance's Sherlock spectrometer, that's scanning habitable environments with Raman and luminescence for organics and chemicals, for those keeping score, hit it with ultraviolet light, the surface didn't just glow, it lit up like a Christmas tree. Sherlock isn't just a fancy flashlight, it's a sophisticated instrument on the rover's robotic arm, designed to detect organic compounds and minerals altered by water using a laser, cameras, and spectrometers. It basically zaps the rock with a UV laser and then analyzes the light that bounces back, giving us a chemical fingerprint of the material. And what a fingerprint it found! We're talking organic carbon, sulfate, phosphate, and these eerily ghostly concentric rings that geologists immediately and quite fittingly nicknamed leopard spots. This combination alone is enough to raise an eyebrow, but the deeper analysis of the core sample, Sapphire Canyon, is where things get truly wild. Down core, the team discovered graggite, an iron sulfide mineral. On Earth, microbes often manufacture graggite when they breathe sulfate instead of oxygen. It's a hallmark of anaerobic microbial metabolism. Right alongside it, they found tiny nodules of vivianite, an iron phosphate that typically forms when organic goo decays in low oxygen water. Vivianite is frequently found in Earth sediments, peat bogs, and around decaying organic matter, often forming where microbes reduce iron in water-rich sediments. So let's put those three together. Organic carbon, the building blocks of life, graggite, a microbial byproduct on Earth, and vivianite, formed from decaying organic matter in low oxygen water. And all of this is arranged in these distinct repeating leopard spot patterns. If you saw this exact suite of chemical and mineralogical evidence on Earth, you wouldn't hesitate. You'd be looking at a textbook microfossil factory, a clear fingerprint of microbial life. The combination of these minerals, appearing to have formed through electron transfer reactions between sediment and organic matter, is a significant potential biosignature. These findings suggest that the chemical reactions in this rock could have supported microbial life billions of years ago. Could chemistry fake the same story? Now, before we all start practicing our alien greetings, let's get real for a moment here. This is science, and science demands skepticism. Could purely non-biological or abiotic chemistry conjure up the same compelling narrative? Absolutely. It's a valid question, and one scientists are rigorously exploring. Sure, if you dump iron, sulfur, and phosphate into a hot, acidic lab beaker, you can absolutely cook up graggite and vivianite without a single living cell in sight. There are known geological processes that can produce these minerals. For instance, processes like serpentinization, which involve water, carbon dioxide, and the mineral olivine, common on Mars, can generate iron sulfides and other compounds. However, and this is a crucial however, the conditions required for these abiotic formations often don't match what Perseverance found in Chayaba Falls and Sapphire Canyon. The rover's instruments measured the host rock's formation temperature at less than 90 degrees Celsius. That's pretty cool, geologically speaking. What we don't see are any signs of the scorching hydrothermal vents or the corrosive acid seepage that would typically be needed to forge these specific minerals through purely non-biological means. In plain English, the non-biological recipes we know for making these ingredients just don't match the kitchen we're seeing on Mars. While it's theoretically possible to make vivianite abiotically, especially if you have macromolecular organic carbon and ferric iron-rich mud, the production of greggite is a much tougher ask without biology. The reaction between sulfate and organic matter at room temperature is incredibly slow. So slow, we don't typically observe it happening in natural Earth environments without microbial help. This doesn't definitively prove life, not yet, but it does something equally important. It removes the easiest get-out-of-jail-free card for the abiotic explanation. The scientific team behind the findings has published a peer-reviewed paper stating they found no strong evidence for abiotic formation pathways for these patterns. While this doesn't definitively rule out every non-biological possibility, it significantly strengthens the biological hypothesis by eliminating the most straightforward alternatives. The uniqueness of this combination, especially the leopard spot textures with their specific mineral composition, makes an abiotic origin increasingly difficult to explain. The implications are that if these minerals did form through microbe-like metabolisms, it would extend Mars's habitability into a period when Jezero was still wet and chemically active. NASA's confidence thermometer. To help navigate these incredibly complex and potentially world-changing discoveries, NASA employs a very sensible tool called the cold scale, the confidence of life detection. Think of it as a scientific thermometer, ranking claims of extraterrestrial life from 0 to a definitive 7. It's designed to provide a standardized method for assessing claims and communicating findings clearly to both the scientific community and the public. This scale is critical for managing expectations and preventing headlines from running wild, which, let's be honest, they're always eager to do. So, where do these recent Martian readings from Chayava Falls and Sapphire Canyon sit on this crucial scale? They're currently at a solid 4, intriguing but not conclusive. That might sound a bit anticlimactic after all this talk of biological hints, but a 4 is actually a huge deal. It means we've detected a possible signal, and we've ruled out a significant number of non-biological explanations. It's a strong indication that something truly special is going on. To hit a 7, the absolute highest rung, we need 2 things that Earthbound labs are exceptionally good at. Things a rover on Mars, no matter how advanced, simply can't do with the necessary precision: centimeter scale slicing and isotopic dating. Centimeter scale slicing. Imagine trying to find a needle in a haystack, but the haystack is a rock and the needle is a microscopic fossil. On Mars, Perseverance can drill core, but it can't meticulously slice that core into ultra-thin sections, examine individual mineral grains under powerful electron microscopes, or hunt for the incredibly subtle morphological clues of microfossils. That requires the specialized equipment and controlled environments of terrestrial laboratories. Isotopic dating and chirality. This is where we get into the truly definitive biosignatures. Life as we know it has a strong preference for certain isotopes of elements. For example, biological processes preferentially incorporate the lighter isotope of carbon, carbon-12, over carbon-13. Measuring these ratios in organic molecules can tell us if the carbon came from biology or from a volcanic outgassing event. Even more compelling is the concept of chirality. Many organic molecules, like amino acids, the building blocks of proteins, exist in 2 mirror image forms, like your left and right hands. On Earth, life almost exclusively uses left-handed amino acids. Finding a dominance of one-handedness in Martian organic molecules would be a powerful, almost undeniable biosignature. The cold scale is there to ensure scientific rigor and prevent premature declarations. It requires a series of stringent tests to progress up the ladder. While a 4 indicates robust, compelling evidence, it's the meticulous, multi-pronged analysis back on Earth that will push us towards that coveted 7. The data, however, is running as fast as it legally can towards that goal, and the scientific community is buzzing with the level of excitement that truly feels unprecedented. What about life today, not yesterday? Okay, so we're talking about ancient microbial life billions of years ago when Mars was a wetter, warmer place. But what about now? is there life on Mars today? Let's be brutally honest. The surface of modern Mars is an absolute nightmare for life as we know it. It's a frigid wasteland with average temperatures plummeting to minus 60 degrees Celsius. The radiation levels are off the charts, so intense that they'd sterilize hospital instruments in no time, blasting apart complex organic molecules. And the atmosphere, it's so incredibly thin, mostly carbon dioxide, that liquid water can't exist stably on the surface. It either freezes instantly or boils away at blood temperature due to the low pressure. It sounds like a death sentence for any organism. Yet, nature is full of surprises, and life on Earth is incredibly tenacious. Every winter, in the desolate, bone-dry valleys of Antarctica, we find microbes that survive conditions that are colder, drier, and more irradiated than almost anywhere else on Earth. They don't just endure, they thrive inside rocks, shielded from the worst of the elements. These are extremophiles, and they teach us that life finds a way even in the most improbable niches. Could something similar be happening on Mars? It's certainly possible. If ancient life did exist, it could have migrated underground as the planet's surface became inhospitable. Deep beneath the Martian soil, shielded from radiation and warmed by geothermal heat, pockets of liquid water might persist. Here, microbes could be living off hydrogen and sulfate, much like Earth's deep biosphere does, kilometers beneath our feet, completely independent of the sun. Perseverance can't drill that deep, but the possibility remains tantalizing. And then there's the methane. Perseverance and other missions before it have spotted reoccurring methane plumes in the Martian atmosphere. They spike in summer and then mysteriously vanish in winter. This seasonal variation is incredibly intriguing. Methane can definitely be geological in origin. It can be produced by water-rock reactions like serpentinization or released from ancient subsurface clathrites, ice cages trapping gas. But on Earth, over 95% of atmospheric methane comes from life, specifically from microorganisms called methanogens. The fact that these plumes are seasonal, appearing when the planet is warmer, just adds to the biological intrigue. It's a maddening coincidence, a persistent whisper of present day life that we can't quite confirm or deny. While some studies have tried to rule out geological sources like wind erosion releasing trapped methane, the puzzle remains. So, while we have no definitive proof of current life, the search for it continues, both directly through instruments looking for organic compounds and indirectly through atmospheric clues like methane. The conditions on Mars today are extreme, but Earth's extremophiles offer a blueprint for how life might persist in such a challenging environment. The sample return countdown. This brings us to the ultimate game changer, the Mars Sample Return mission. Perseverance has been doing an incredible job, but there's a limit to what a rover on another planet can achieve. The real breakthroughs, the definitive answers, will come when those Martian rocks are brought back to Earth. Perseverance has meticulously sealed Chayava Falls, Sapphire Canyon, and over 20 other companion cores in ultra-clean, hermetically sealed titanium tubes. These aren't just any containers, they're designed to prevent any terrestrial contamination while preserving the Martian samples in pristine condition. This is where the meticulous planning of decades comes into play. The Mars Sample Return campaign is arguably the most ambitious robotic space mission ever conceived, a joint effort between NASA and the European Space Agency. It's a multi-stage relay race across the solar system. First, Perseverance collects and caches the samples. Then, 2 small helicopter drones have already tested the flight path and collection techniques, mapping out the route the Mars Sample Return lander will follow. The plan is for this lander to touch down in Jezero Crater around 2031. It will carry the Sample Fetch rover, a smaller rover, and crucially, the Mars Ascent Vehicle, MAV. The Fetch rover will retrieve Perseverance's cached samples and bring them to the MAV. The MAV will then blast off from the surface of Mars, becoming the first rocket ever to launch from another planet, carrying those precious titanium tubes into Martian orbit. Once in orbit, the samples will be rendezvoused by the Earth Return Orbiter, ERO, which will capture the sample container and securely place it inside a specialized Earth entry system. If all goes according to plan, we will have 0.5 kilogram of genuine Martian rock and regolith on Earth before 2036. And that's when the real scientific party begins. Imagine the world's most advanced laboratories, equipped with instruments of unparalleled precision, all focused on these tiny pieces of Mars. Scientists worldwide will slice them thinner than paper, meticulously analyze their mineralogy, and hunt for the most subtle biosignatures. They'll perform the high-resolution imaging and elemental mapping that Sherlock and Pixel can only hint at. They'll hunt for amino acid chirality, looking for that telltale preference for left-handed molecules. They'll conduct isotopic ratio analysis, examining the carbon, sulfur, and nitrogen isotopes to discern biological processing from abiotic origins. They'll even look for complex organic molecules that might be the remnants of cell membranes or other biological structures. If the biosignature tally climbs from a compelling 4 to a definitive 7, the discovery paper, the scientific announcement that life once existed on Mars, would make the moon landing look like a mere footnote in the grander story of humanity's cosmic awakening. It would be a moment that transcends science, echoing through history for millennia. Don't you want to be right there when that history is made? Smash that subscribe button if you want to be the first to know when those samples finally touch down. The return window is only 8 years away, and the science is accelerating faster than the rockets that will bring us those answers. Why this time feels different. We've been here before, haven't we? The tantalizing headlines, the breathless speculation, the proof of life on Mars pronouncements that, under closer scrutiny, ultimately crumbled. It's important to acknowledge that history to understand why this time, with Chiava Falls, Sapphire Canyon, and those leopard spots, feels genuinely different. Let's rewind a bit. The 1996 Allen Hills meteorite, ALH 84001. This Martian meteorite, found in Antarctica, made global headlines when NASA scientists announced they'd found what looked like fossilized microbial structures and organic compounds within it. President Bill Clinton even gave a speech about it. But the evidence was hotly debated. Critics argued the microfossils were too small to be living cells, and the organic compounds could have formed abiotically or been terrestrial contamination. Later studies, with more advanced technology, concluded that the organic molecules were indeed formed by abiotic processes, essentially geology, not biology. A fascinating discovery, but not life. The 2004 methane whiffs. When early missions detected plumes of methane in Mars's atmosphere, excitement surged. As we discussed, methane on Earth is overwhelmingly biological. But again, geological processes can also produce methane, and the source remained ambiguous, lacking definitive biological markers. The mystery persists, but it hasn't translated into a confirmed biosignature. The 2018 seasonal water streaks. Dark streaks appearing seasonally on Martian slopes, called recurring slope lineae, or RSL, were initially thought to be evidence of flowing briny water. The idea of liquid water on the surface, even briny, was exhilarating. However, further research suggested they were likely caused by dry granular flows, like dust avalanches, rather than actual flowing water. Each of these moments taught us something invaluable about Mars and the challenges of detecting extraterrestrial life. But critically, each lacked multiple independent chemical lines of evidence pointing unequivocally to biology. They were often single, ambiguous signals that could be explained by non-biological phenomena. Chiava Falls, however, is a different beast entirely. It presents not one, not two, but 4 separate biosignature classes within a single core sample. We're talking organic carbon, vivianate, greigite, and those distinct leopard spot textures all occurring together in a way that, on Earth, is strongly indicative of microbial activity. This statistical unlikelihood, this confluence of independent indicators, is what has even hardened skeptics, calling it eyebrow-raising. It's not a single data point. It's a symphony of signals all playing the same biological tune. The rigor of the scientific process further underscores this difference. When the rover team's paper was submitted to the prestigious journal Nature last month, reviewers, as they should, demanded an extra round of tests. This isn't unusual for groundbreaking claims. What is unusual is that the data passed with flying colors. That level of scrutiny and subsequent validation hasn't happened for a potential life detection claim since the Viking landers in 1976. The fact that the evidence held up under such intense peer review speaks volumes about its robustness. This time, the evidence isn't just intriguing, it's stubbornly, compellingly there. The philosophical jackpot. If these findings are confirmed, if we definitively prove that microbes once thrived on Mars, it won't just be a scientific discovery. It'll be a profound philosophical jackpot, a profound reorientation of humanity's place in the cosmos. For centuries, a persistent question has haunted us. Is life a cosmic fluke, a one-off miracle unique to Earth? Or is it a fundamental, inherent property of the universe, a cosmic habit waiting to happen wherever the right conditions coalesce? If life arose independently on Mars, even if it's long extinct, it provides powerful evidence for the latter. It suggests that the transition from chemistry to biology isn't a miraculous exception, but a natural, perhaps even common outcome when water, rock, and time intersect in a favorable environment. This single realization would rewrite astrobiology textbooks overnight. It would dramatically shift the odds in favor of life on the countless exoplanets we're currently discovering around distant stars. The Fermi paradox, which asks why, if life is common, we haven't seen any evidence of it, would suddenly have new parameters. It wouldn't necessarily solve it, but it would certainly reshape our understanding of its premise. The implications ripple far beyond science. It would ignite theological debates, forcing a reevaluation of anthropocentric worldviews that place humanity at the absolute center of creation. It wouldn't necessarily contradict faith, but it would certainly expand its boundaries, pushing us to consider a universe teeming with diverse forms of existence. It challenges our sense of uniqueness and makes us rethink our place in the cosmos. In short, finding extinct microbes on Mars is, in many ways, bigger than finding living penguins in Antarctica. Why? Because the penguins, as delightful as they are still Earth life. They don't tell us anything fundamental about the universality of life's origin. Martian microbes, if confirmed, would prove that the transition from chemistry to biology is universal, that abiogenesis isn't a one-trick pony. It would be an affirmation that we are part of a much larger, more biologically rich universe than we've dared to imagine. It would be a paradigm shift, an awakening to the true scope of cosmic possibility. How to stay sane while history unfolds. In an age of instant information and sensational headlines, it's incredibly easy to get swept up in the hype, or conversely, to become cynical about every new scientific announcement. When it comes to something as monumental as the search for life beyond Earth, it's crucial to cultivate a healthy dose of scientific literacy and critical thinking. Here's how to stay sane, informed, and genuinely excited as this incredible story continues to unfold. 1. Don't binge every rumor. Resist the urge to believe every clickbait headline that screams, "NASA confirmed life." Science is a process, not a series of definitive pronouncements. These stories often oversimplify or exaggerate claims. 2. Go to the source. Always. The best way to get accurate information is to follow primary sources. That means looking at official mission websites, press releases from the space agencies themselves, and if you're up for it, the peer-reviewed scientific papers. NASA JPL. Check the official NASA Jet Propulsion Laboratory website for Perseverance mission updates. NASA JSC Astromaterials Twitter feed. This is where the experts who handle the samples, when they return, often share insights. ESA Sample Return blog. Keep an eye on the European Space Agency's updates for the critical return phase. Open access paper cache on Sherlock's public server. Many scientific papers are made publicly available. Look for the actual research, not just interpretations of it. Credible science news outlets. Seek out journalists with a strong science background or reputable publications known for their accurate science reporting. They will often cite the original research and interview multiple experts, not just those involved in the study. 3. Understand the cold scale. Remember NASA's confidence of life detection scale? When someone claims NASA confirmed life, immediately ask yourself, did cold just tick past 5, 6, or even 7? Until it hits those higher numbers, the honest headline remains what you heard today. Strongest evidence yet, but the verdict is pending. The cold scale is designed to prevent crying wolf and making overly cavalier claims. 4. Look for nuance. Science is rarely black and white. Be wary of articles that present definitive conclusions without caveats or discuss only a single line of evidence. Good science reporting will acknowledge uncertainties, discuss alternative explanations, and explain the limitations of the current data. 5. Check for peer review. Reputable scientific findings are published in peer-reviewed journals like Nature or Science. This means other experts in the field have scrutinized the methods and conclusions. If a claim isn't peer-reviewed, approach it with extra skepticism. This isn't just a story for scientists. It's a story for all of us. But engaging with it thoughtfully, critically, and patiently will ensure that we truly appreciate the magnitude of what's happening, rather than getting lost in fleeting sensationalism. All right, Air Chair astrobiologists, it's your turn. Drop a comment below with your over-under odds that the Mars sample return mission comes back positive for biology. What's your gut feeling? What's your educated guess? I'll pin the boldest, most well-reasoned prediction a year from now, and we'll see who eats humble pie when those rockets land. Let the cosmic betting begin. Conclusion. The take-home truth. So, let's bring it all back home, shall we? We have not, today, proven life on Mars. Not definitively. But for the first time in humanity's long, curious gaze at the red planet, we can say, without a shred of hyperbole, that the most likely explanation for 3 freshly drilled rocks from Jezero crater is ancient microbial metabolism. It's a statement of scientific probability, backed by multiple independent lines of chemical evidence, rigorously tested and peer-reviewed. This isn't speculation born of hope. It's a conclusion emerging from meticulous data. And the next step isn't more speculation. It's a tangible, ambitious, and already in motion countdown timer set for the Mars sample return mission. This is the moment we've been building towards, the culmination of decades of planetary exploration and scientific ingenuity. So, keep watching, keep asking those profound questions, and whatever you do, don't let the universe surprise you without being in the room when the answer finally arrives. Because when it does, it won't just be a scientific triumph, it will be a human one, forever altering our understanding of life itself.